Well, I'm not sure this is what I'm going to give, but anyway, we'll try. So if you start from modular form F, which is primitive of weight k bigger than 2, and if you take P a prime, then we can attach to F a Galois representation. So I'm not going to mention all the names of the people who work on the subject because there are too many of them in this room. So, so we have a Galois representation rho F from, I mean, for me, primitive means new form, eigenform, and so on. It's like for characters, for directly character, primitive. So we have a Galois representation GQ to GL2 of L, where L is going to be a finite extension of QP. And this Galois representation has some properties. So first, it is odd. So the determinant of complex conjugation is -1. Then it is unramified outside the finite number of places, unramified outside S, which is finite. And at P, it is as good as what you can hope, so it is de Rham at P. And then there is a conjecture of Fontaine-Mazer, so a very special case of conjecture of Fontaine-Mazer plus global Langlands correspondence telling you that the converse should be true. So Fontaine-Mazer, let's say. Any row, so this I denote by star. So any row that satisfies star should be a row F. Star should be a row F up to twist by a character. So this is a vast generalization of Taniyama-Weil's conjecture. And since the work of Wiles, so how do we prove this kind of statements? Well, it's, I mean, the proofs that we know of now go as follow. So first you prove it mod P. Yeah? You already have some complaints? The pk is bigger than 2. Ah, okay. The Rham at P with distinct odd state weight. Sorry. Okay, so you prove it mod P. So this is Serre's conjecture, which is now a theorem. Now a theorem. And then what you do is that you try to lift the statement from characteristic P to characteristic 0 by constructing some moduli problem. So you construct deformation spaces, or deformation space, deformations problem. So construct or consider deformation problems. And you put a local condition on both sides, on the Galois side and the modular side. So with local conditions. On both sides. So both sides, I mean Galois sides and modular form sides. And then what you have to prove is that these two deformation problems are in fact isomorphic. So and prove them to be isomorphic. So if you want this to be true, you have to put very good local conditions so that they match really well. And the most difficult thing is to match the local condition at P. So most difficult is match local conditions at P. And that's where the local Langlands correspondence appears. So p-Adic local Langlands. And in fact, the fact that there should be something like a p-Adic local Langlands, so it was in the head of many people, but I mean, it came to have some concrete meaning because Breuil did a lot of work on it, and this work was motivated by the proof of the full Taniyama-Vell conjecture. So he did some computation, and he thought that obviously there was something deeper behind. So what kind of local condition you are going to consider? So to a modular form F, then we know how to associate a representation of the finite group of the Adel. So this representation just is a tensor product, a restricted tensor product of some local representation. And this pi L is smooth. So smooth means locally constant, admissible, irreducible representation of GL2 of QL. So that's 2F. And now when you look on the Galois side, well, for L different from P, what you have is that you have this representation rho FL, which is going to be the restriction of the representation rho F restricted to the absolute Galois group of the field QL, Galois of QL bar over QL. Then we know that this is potentially unipotent. And because of that, one knows how to get rid of this unipotence by adding some monodromy operator. And you get a representation of the Veil-Deligne group of QL, which I will denote by Veil-Deligne of rho F. And one knows how to go back to the Galois representation from here. And this Veil-Deligne representation itself corresponds to this pi L via the usual local Langlands correspondence. Now, when L is equal to P, the situation is a little bit more complicated. So this rho Fp now is not potentially unipotent, it's only potentially semi-stable. So nowadays people would say potentially log crystalline. So is, but I will stick to the old terminology, potentially semi-stable. And one knows how to classify this kind of representation. So there is something that Fontaine introduced, which is called the DPST of this rho Fp. And what is this DPST of rho Fp? Well, it consists of two things. It consists first in a representation of the Veil-Deligne group at P of rho F, which corresponds via the local Langlands correspondence to this pi P. But there is some extra data that allows you to recover this representation. And this extra data is a filtration on this space. So this is a two-dimensional space, and you have a filtration. So plus something which is called an admissible filtration with jumps at 0 and k minus 1. So with the admissible filtration, with the jumps at 0 and k minus 1, you can produce an algebraic representation of GL2 of QP out of it, and it's going to be the k minus 1 symmetric power of the standard representation. But the big question is, how do you get the filtration? I mean, from this data, you're only going to get this vectoring representation and the jump in the filtration, the Hodge state weight of the filtration of the representation, but you don't get the filtration, and so you cannot recover this Guerrero representation. And so this was the starting point of Breuil. And Breuil asked, well, is there any way, any p-Adic way of encoding the filtration on the GL2 of QP side? And so the conjecture that he proposed was the following. That in order to recover the filtration, you should consider not at this space which has no topology, but you should look at completion of this space, not of this space, of the tensor product of these things. So you look at, is it okay if I write here? Do I mean k minus 2? Maybe I mean k minus 2. Yeah, it's right. It's k minus 1 minus 0 minus 1. So k minus 2. Okay, so the conjecture of Breuil was take the following shape. Is that if you look at the admissible filtrations on this space, W dp of rho f, or of rho f, let's say, they should correspond in a natural way to admissible completions, which some things which I will define now, completions of this representation of GL2 of QP that you get by tensoring the two ones which are there, so of sim k minus 1, k minus 2, tensor pi p. And this would be one of the incarnation of this p-Adic local Langlands correspondence. Okay, so what do I mean by admissible filtration, admissible completions? So I will define, so G is GL2 of QP. And I will define the category of representation of G that we want to consider. And so they are going to be representation like this. So it should consist of an L Banach, so an L vector space with a structure of p-Adic Banach space, L Banach pi, with a continuous action of GL2 of QP plus continuous action of G. So that's the first thing. You want it to be unitary. So unitary means that you can choose the unit ball here to be stable by the action of G. So choose, I mean, you can always change the norm so that the unit ball, we not pi naught, is stable by G. You want a central character. Omega pi. And what you want more is that this representation should be admissible, meaning that when you look at the reduction mod p, pi 0 bar, then it should be admissible in the usual sense, which means that if you look at pi 0 bar by any compact open subset, it should be finite length, finite, what do I want? Should be a finite OL module. So bar means the reduction mod p. So you take you take a lattice and you just reduce it mod p. So it should be finite length. So it should be finite OL module. Okay, so we want to look at completions of this representation which have these properties here. So central character will be for free because you have a central character here, but all the rest you want. And one last thing that Breuil asked is that, well, you can look at pi bar 0 and you can look at its Siemens simplification. And he wanted it to know, I mean, corresponds to when you look at rho fp, you reduce it mod p, and you semi-simplified by some mod p local correspondence that he defined. Mod p local Langlands. Okay, so that was the requirement that Breuil wanted of his local Langlands, p-Adic local Langlands correspondence. And so I will explain to you that we are going to do, in fact, much better. So we are going to construct a functor pi goes v of pi. So pi here means a representation of GL2 of QP. And this v of pi is going to be a Galois representation of GL2 of Galois, absolute Galois group of QP. And this functor goes through the theory of phi gamma modules. So via phi gamma modules theory. So this is something that Fontaine introduced to classify these Galois representations. Okay, so maybe I should first remind you what p-Adic numbers are. So I've what?
Pi is something.
Yeah. Pi. I mean, pi should be an element of this, or it will be a torsion representation. So, okay, so it will be both. I mean, in fact, this functor will first take torsion objects here to torsion objects here, and then you have to take projective limits and invert p, and you will get the one you're really interested in. Okay, so first let me remind you things about p-Adic numbers. So I put a drawings of p-Adic numbers here, so I was not going to write it in front of you. So this is the tree of 3-adic numbers. Okay, so you start by putting it z mod 1z, so there is only 1 point. Then you have 3 mods, z mod 3z, so you have 3 points here, and so on. And at the end, you get z3 at the projective limit of these things. And now, if you take one of the edge of this tree, one of the then each of these edges correspond to an open subset of Z3. Okay, and if you write the element of Z mod 3 to the nz in base 3, then what you get, what you will see appear is the expansion in base 3 of your 3-adic numbers. Okay, so that's for Z3. And then you have the same thing for Q3. So for Q3, what you get, so here is still Z3. So you see you have the edge of Z3. But this is also the tree of GL2, of PGL2 of Q3. And so you have an action of PGL2 of even GL2 of Q3 on everything. And here I put some representatives. So you have representatives of GL2 of Q3 modulo GL2 of ZP times the center. Z of the center. And these representatives are of the shape P3 to the n, something 0, 1. Okay? And here I put the identity here. And then from here you get a bijection between the open subset of, the basic open subset of pi 1 of Q3 and these representatives. And so you get this representation of these p-Adic numbers. So I'm going to use it later on. And now I have to recall some facts about phi gamma modules. So phi gamma modules are extremely simple objects. So you start by defining the following ring. So OE plus is just going to be OL double bracket T. And then you define a ring OE by starting from OE plus mod P to the n. Then you invert T and you take the inverse limit. So it's the p-Adic completion of OE plus of when you invert T. And there is one very nice interpretation of this ring in terms of p-Adic functional analysis. So I'm sorry for people who already heard me many times on this subject, but this is one interpretation that I like particularly, so I'm going to give it to you. So you have a natural exact sequence where here you have the measures on ZP with value in OL. Then you have OE. Then here you have the continuous function on ZP with values in OL equal to 0. And so this one is just OE plus. And this one is OE mod OE plus. And what are these isomorphisms? Well, the first isomorphism, if you have a measure, you can define its Amis transform, the integral over Zp of 1 plus t to the x mu of x. So you start from a measure, you get a power series in t, and this gives you an isomorphism. Which one? 0, yeah, it's because measures are distribution of, how do you say, of order 0.
So you want measures?
Yeah, I want measures. These are measures. And then you have the functions here. So you take an element z in OE, and you can attach to it a function on Zp, just defined by phi f, phi z of x, to be the residue at 0 of z 1 plus t to the minus x dt over 1 plus t. And the fact that you really get all the continuous function in this way, it's clear that you get a continuous function. And the fact that you get all the continuous function is just a rephrasing of Maller's theorem on Maller's expansion of continuous functions. Then, well, this is something that I use all the time to think about these objects. So I like to put it here. And now you have an action of, you put an action of two things on your ring. So you put a Frobenius just by insisting that phi of t is equals 1 plus t to the p minus 1. And you want it to be a morphism of ring. And then you define an action of gamma. So gamma is to be thought as a Galois group of qp of mu p infinity over qp, which is isomorphic to zp star via the cyclotomic character. And if you have an element A here, you write sigma A, its inverse image here. So sigma A is just the element of gamma, which is mapped to A by a cyclotomic character. And what you want is that sigma A of t is 1 plus t to the A minus 1. And what I claim is that with these actions, in fact, you are not so far from an action of GL2 of QP. I mean, you are not so close either. But using these actions, you have an action of the following semi-group, ZP minus 0, ZP 0 of 1 acts by the following formula. So it acts on OE. It acts on OE, and this action stabilizes OE plus and the quotient. And the natural action is the following. So if G equals P to the K A B 0, 1, well, G acting on element Z is going to be 1 plus T to the B sigma A of phi to the K of Z. And here you could permute the two because the action of gamma and Frobenius are clearly commuting. And now, well, I don't really need it for the talk, but just to give you an idea of what this formula gives in real life, so on these concrete objects, what you get is that on measures, you have the integral over Zp of a function phi of x G mu. So G is still this one. This is just going to be the integral over Zp of phi of p to the k a x plus b. So exactly the action you would think of. And on function, it's the same. So if you want phi of g z of x, well, this is phi of x minus b over p to the ka, whenever this makes sense. So if x is in b plus p to the k zp, and it's 0 if not. So just to show you that by using this phi and gamma, you can recover very natural actions on measures and functions. Okay, so what is a phi gamma module? So that will be for this talk. So phi gamma module D by definition, it's going to be an OE module of finite length. Plus two actions. So commuting action of phi and gamma, commuting semi-linear actions of phi and gamma. So that's a phi gamma module. Right? And then you say that it is étal. D is étal. If you look at its image by phi, it generates D. I mean, phi is not bijective, so that's the best you can hope. And why do we care? It's because of Fontaine's equivalence of category. So you have the following theorem of Fontaine, which tells you that these étal phi gamma modules are in equivalence of category with the finite length representations of GQP, so finite length OL module plus an action, continuous action linear action of GQP. And in the end, the local Langlands correspondence is supposed to produce objects here. So this category I call phi gamma torse. And this one I called rep torse of GQP, because these are tangent. And so as usual with Fontaine's theory, you have a magic ring that allows you to go from one side to the other. And so we have a ring A with actions of GQP and phi, which commutes. And what you do, if you have a D, if you have a V, you define the D of V to be, well, you extend the scalar to A, and then you take the fixed part by the kernel of the cyclotomic character. And going in the other direction, if you have a D, you define a V of D in the same recipe. So you extend scalar to A, except that because I have assumed that everything was L linear, I have to put an OL here over OE, tensor D, and then you take fixed part for Frobenius. And I am not going to define this ring because I will not need it in this in this talk, but that's always the way it works. And so for this talk, it is not important to understand how this functor is constructed, but for many of the proofs, it will be important to understand how this works.
How does the unitarity translate?
Excuse me?
The unitarity, how does that translate?
Well, it's not yet here. I will tell you when it comes. Because now there is still no...
You can't, so you need more structure.
Now there is no action of GL2 of QP on these things, okay? There is nothing. There is... action of GL2 of QP is going to come. Anyway, I mean, unitarity is just used so that you have a unit ball that you can reduce mod p to the n. That's how it's going to appear.
So the real one will be not p to the n?
Yeah, so the construction I'm going to give right now is going to be a construction mod p to the n, and then you take projective limit, and then you will get construction which is not mod p to the n. So anyway, so now we are here. So we know that that representation of GQP corresponds to phi gamma modules, okay? Now my phi gamma modules, what they are finitely generated OE module. And if you look on this picture, it's clear that OE has a lot of things to do with ZP. You cannot deny this fact. On one side, you have the measures on ZP. On the other side, you have the continuous function on ZP. Okay. So on the other hand, if you start from a representation of GL2 of QP, you have some objects that lives over QP or maybe pi1 of QP. And so there is an obvious way to define this local Langlands correspondence. And it took me a long time to find out. So the obvious way is the following. You start with LL, local Langlands, then you curve it, and then you go to this side. And so you have a nice pair of scissors that is going to cut the tree along the edge corresponding to this tree, and then you're going to be left with the Z3 part. So how do you translate this in mathematical terms? In the following way. No, it took me quite a long time to understand that this is what was going on. So mathematically, what you do is the following. So I'm going to construct a functor starting with a pi. I'm going to construct a v of pi, except that I'm completely cheating because I'm not going to construct a v of pi. I'm going to construct a phi gamma module, okay? And then Fontaine's equivalence of category is going to do the rest of the work for you. So first, what are the objects? So let me define what is the torsion representation of G, R. So these are going to be pi's on which you have an action of G. So this action of G is locally constant. It has a central character. And its finite length as OL of G modules. OL of G module. Okay, and this, all these conditions put together, it implies that it is admissible in the previous sense. Meaning that if you take the fixed point under a compact open, you get something of finite length over OL. And basically, these elements here are what you get if you start from some unitary things admissible and you reduce mod p to the n. It's not completely true, but but anyway, this is what you want to consider. And if you have such a pi, you can look at its dual, which is just hom of pi. So it's a Pontryagin dual. So it comes with an natural action of G. And then you have to choose a W inside pi, which is a finite length OL module. So it's a finite OL module. You want it to be stable by GL2 of ZP. And what do you want else? You want on top of it that it generates pi. So this exists because I have imposed that this is finite length. So there is no problem for the existence of these things. And so what does it mean here? It means that you can write pi as a quotient of the compact induced representation from kz to g of this W. It means that you take a function with compact support, compactly induced. K is GL2 of ZP. Yeah, here it was any K. Now K would be this one. And so if you look at this picture, it means that here you would put W, and then you would put all the translate of W here, and this would cover completely your representation pi. And then from here, you define what I call D plus W of pi, which is the thing that ignore everything which is not in ZP, okay? And ignore everything that is not in ZP means the following. You take the mu in the dual, and you want them to be orthogonal to anything of the type p to the n b0 1 z, W. If if you are not in ZP, meaning that if p to the n ZP b plus p to the n ZP is not inside ZP. Okay? So on this picture, it means that you take something which is going to be 0 everywhere outside of here. And so it's very easy to verify the fact that this is stable under the action of the semi-groups that I erased. So under ZP minus 0, ZP 0, 1. And because of that, it is naturally a phi gamma module over OE plus. So this implies that it is phi gamma module over OE plus. And so what are the structure, phi, gamma, and so on? So phi is just the action of P0, 0, 1. Sigma A is just the action of A0, 0, 1. And now you need to know what T is, but T is just going to be 1, 1, 0, 1, minus 1. So it's an element of the group algebra. Yeah, so if you start from the Steinberg representation, for example, in order to understand what's going on, so I assume that pi is a Steinberg. So which means that this is the locally constant function on pi 1 of QP with value in the residue field of L modulo the constant. And you can take W. So because of that, you can view them as also the locally constant function with compact support on QP, because you mod out by the constant. You just have to subtract what is going on near infinity. And so you can also view that as locally constant function on QP with value in KL. And of course, here you don't see the action of GL2, but that's not really a problem. So W is going to be the subset generated by the characteristic function of I plus PZP from I equals 0 to P minus 1. So what is the translate of W by one of the elements which are here? So if you look at so P to the n B0, 1 acting on W, then you get the same sum, KL 1 over, well, it's B plus P to the ni plus P n plus 1 ZP. So what does our construction of just cutting at the edge Z3 correspond to? So it's just going to take the n for which n is positive here, and B is in ZP. And so you will see that you recover in this way all the continuous function on ZP, locally constant function on ZP. Okay? And so if you take the dual of this part, what you get are the measures on ZP, and so it will be OE plus. Okay? So what I did was not exactly to cut that. I imposed that it was 0 outside of here. So there is some interaction between this part and this part. And this interaction is just that the characteristic function of Z3 appears here. So what you are going to get is that this dW plus of pi, this is the set of mu of measures on ZP with values in KL now, such that the integral over ZP of mu is equal to 0. So you have one condition. And by the isomorphism I wrote before, this is isomorphic to T KL double bracket T. Okay, so it's not a very mysterious object. And so now what is the theorem? So the theorem is the following, is that you define d of pi to be, you extend scalar from OE plus to OE, d plus W of pi. So pi here is an element of rep torse of G. So it's a torsion representation of GL2 of QP. Then this thing is an element, is a phi gamma module of torsion phi gamma module, and which is independent of the choice of W. Of W. So that's the first thing. Second thing is that this functor pi goes to d of pi. This is exact contravariant. And now if you want something which is covariant, you just you dualize. And so what you do is that you associate to it this following Galois representation. So you take Fontaine's V, but you take its state dual. So it's just for normalization of d of pi. And then you get a covariant exact functor from the category rep terse of G to the category of torsion Galois representation. So is exact covariant from rep torse of G to rep torse of GQP. Okay, you see it's completely harmless. You have not done anything. And basically, I mean, this ring does all the work for you. And so maybe I should say some things. Yeah, maybe now once you have this, you can take projective limits and invert P. And so projective limit and 1 over P. And then you get the same functor V going from the representation of G to representation of GQP. So now these are L vector spaces. And these are unitary, admissible, and so on representation of GL2 of QP. Yeah, so in this theorem, everything is totally obvious except one thing. So the one thing is this, in here there is some finiteness condition here. So you have finite length OE module, and that's the only thing which is not obvious. So I have one proof that uses the classification of irreducible mod P representation of this group, G. And yeah, and so I should also point out that this Caesar functor is easy to construct, and so it has been generalized by Schneider and Vigneras, not Schneider and Teitelbaum. But their problem is that they cannot prove any finiteness statement of this kind. So up to now, I mean, there is a functor in bigger generality, but we do not know if this functor is of any use.
Let me repeat my question.
Yes.
Are you using some characterization, you know all the unitary representations, somebody's classified with analog with Bogman in this situation?
No, so the only thing...
Constructing it for these kinds starting with the Steinberg.
Okay. The only thing that...
Picked up every unitary.
Well, I'm picked up every unitary here. See, and the only thing I use is the fact that some people, namely Bartel, Livnet, and Breuil, classified the irreducible mod P representation of G. Okay, that's the only thing I use in this theorem.
So where are you using your unitarity?
No, but the unitarity is just so that you can reduce it mod P. Otherwise, it would make no sense. This step would make no sense.
But then along the way, you know what they are.
No, not yet. I mean,
what are all the representations?
I will in 3 seconds. But it's 160 pages of Pascunas, so. Well, I will not. I will. So my claim is that this V is just realizes the p-Adic local Langlands correspondence. And in fact, it's much better than usual Langlands correspondence because it's a functor So by construction, it is compatible with reduction mod P because it starts with reduction mod P. And because it is a functor, it works very nicely in families. And this is used quite a lot for application and in the proof. And there are some other features which I cannot, where I have no time. So to state the theorem, let me introduce some terminology. So you say that pi, which is supposed to be irreducible, is ordinary if it is a subquotient of some induced representation of a character of the Borel, so end B G of delta, where delta going from B to O L star is a continuous character. And in that case, what you prove easily, so in that case, V of pi, in that case, is of dimension 1 or 0. Or 0. And now the theorem is the following. So here I should point out that, okay, I start from a representation of GL2 of QP, but I don't know at all what I get on the Galois side. It could be of arbitrary dimension. And the theorem is the following. So V gives a bijection between, so irreducible non-ordinary pi, representation of GL2 of QP, and irreducible two-dimensional representations of GQP. Okay, so in a way now you know all the irreducible representation because they come from from this construction. But it's the only way I know how to construct this kind of representation. Okay, so I should, if I'm completely honest, I should say that this is proved for P bigger than 5. For P equals 3, for P bigger than 3, or P equals 2, and the Galois representation V bar non-trivial, so V bar SS not scalar. So surjectivity is okay. And it is proved in a very indirect way. So it was an idea of Kissin that you could prove such a statement because, well, inside this, there are some representations that you can construct explicitly, which are called principal series representation. For this, you can compute the functor. And then from this representation, you can, by analytic continuation, extend it to everything. So that's surjectivity. And then Pascunas, very recently, proved that if you start from such a thing, then the Galois representation that you get is indeed two-dimensional, which was something I tried to prove and I could not. And he proved much more. In fact, what he proved gives a complete description of this category rep of G, of the category of Banach representation of GL2 of QP. So it's quite a beautiful result. And now, what are the applications? So you have a link with the usual local Langlands correspondence, a link with the classical local Langlands. So the link is the following. So if you have a pi then you can associate to pi the sub-representation of locally algebraic vectors. And then the theorem is the following. Pi here is a Banach representation, unitary representation of GL2 of QP. So now I don't look at torsion things anymore. I just look at L representations, Banach representation. And then the theorem is the following, is that p-Alg is non-zero if and only if V of pi, so the representation that corresponds via using this p-Adic local Langlands correspondence, is potentially semi-stable, so is the RAM, with distinct Hodge-Tate weight. Hodge-Tate weights, which I'm going to call A and B. The second part is that in that case you can actually describe what this locally algebraic representation is. So p-Alg is actually equal to well, some algebraic representation, determinant to the power A, tensor sim B minus A minus 1, and tensor what will come out of the usual local Langlands correspondence applied to the dPST of V of pi. So I remind you what I said at the beginning. If you have a DORAM or potentially semi-stable representation which is the same, then you have a dPST of V of pi, which gives you a representation of the Veil-Delin group. You can apply to it the usual local Langlands correspondence. You get a smooth representation, locally constant, and you tensor it with something which is algebraic. You get a locally algebraic representation, and this is exactly this one. Okay, and then as a consequence of 2 and Pascunas theorem, then you get that indeed the completions of this one corresponds to admissible filtration on that. So you get Breuil's conjecture, which I mentioned at the beginning, is true. And let me finish by some applications to Fontaine-Mazur conjectures. So there are some applications to Iwasawa theory. So I'm not going to explain it. So this is some results of Emerton, Pollack, and Weston. And why do you expect to have some application to Iwasawa theory? So as you have a triangle which is very inspiring. So if you have a D, you have a V which is attached to it by the local Langlands correspondence, and you have a D which is attached to it by Fontaine, like this. And now you can look in the dual at the element which are fixed by P001. Then what you prove easily that in terms of D, there are just element D which are fixed by some psi, which is some inverse to phi defined by Fontaine. And this is some Galois, some Iwasawa module attached to V. And so you have this triangle here. And so the point is the following, is that this here, I put equal, but in fact it's an isomorphism. And this isomorphism, when you when you take a nice basis of these things, is what is going to pop out p-Adic functions. So that's p-Adic functions. So this is some way of rephrasing Perrin-Rioux's machine to produce p-Adic functions. So in this way, you hope that by looking at this subspace of the dual, you're going to be able to describe the Iwasawa module, and then you're going to be able to say many things about p-adic functions. And now the most important application is to Fontaine measure. So this is not due to me, this is due to Emerton and to Kissin. So applications to Fontaine measure. So that's Emerton, Kissin. So they have two different methods that give the application. And so their application says that Fontaine measure is okay if the following conditions are satisfied. So you need p bigger than 3. You need that rho bar is not dihedral. I think so. And you need a local condition at p, so rho bar at p, restricted to GQP, should not be omega 001 twisted by some character. So omega is the mod p cyclotomic character. And so maybe let me give you some remarks about the proofs of Emerton and Kissin. So Emerton, to prove his results, only needs a part of this theorem. So he only needs part 1, that if you have some locally algebraic vectors, then your representation is the RAM and vice versa. So if your representation is the RAM, there is some locally algebraic vectors. So Emerton just needs 1. Of the theorem. Kissin needs 2, which is stronger. And now the proof of 2, in fact, I cannot prove it by purely local methods. I have to use global methods, and I have to use Emerton's work. So, so it needs 2. And the proof of 2. So in this the case where this part here is a supercuspidal. So in the supercuspidal case, needs Emerton's work. So it goes as follows. I mean, you prove that p-Adic local Langlands varies in family, and so and then you have another result of Emerton that tells you that if you have local algebraic vectors, then your representation comes from a modular form. So that was a classification of yes, and so Kissin in his strategy could make it work completely in the non-supercuspidal case. So because in that case you can actually prove directly, compute directly the locally algebraic vectors. You don't need Emerton. You can do a really direct computation here. Okay, so maybe I stop here.